Hello, everyone. Today is August 10th, 2022. My guest today is Professor Ashkan Ashrafi. Ashkan is a CEO of Topolonet and professor at San Diego State University. Thank you for coming on the podcast, Ashkan.
Thank you, Kurush, for having me.
So, what is Topolonet?
It's a startup company that my colleagues and I founded actually 5 years ago. But we have been doing a lot of research on a very important topic in electric power grids. Basically, the problem that we attacked was an unsolved problem in academia for, I would say, more than a decade. And the problem is this. In power grids, we usually have the topology of the grid. And the topology means the connectivity, the way that the grid is connected, and the parameters of the grid. For example, we have a transmission line between a power generator, a nuclear power plant, or another power generator, and a load somewhere like maybe 100 miles away. So the cables, the transmission lines, they have parameters like impedances, stuff like that. So we usually know the nominal value of the parameters and how the grid is connected. And then based on that, there is an analysis, which is called state estimation. A computer software, a rather complex computer software, estimates the voltages, the currents, and the other parameters of the grid from the connectivity and the parameters that we have, and from the limited measurements that we have over the grid. So that has been basically the way that the grid can be observed.
What is the standard for that software?
Well, there are different methods. Basically, they solve a bunch of equations. They are called power balance equations. And these equations are nonlinear, so they have to use numerical methods, for example, Newton-Raphson method, and the other methods to solve these nonlinear problems, equations. But what we did in Topolonet is the reverse. So, and as I said, that was an academic problem for more than a decade, and nobody could solve that. So we looked at the situation where we have the measurements, like the voltages and powers, and we want to find first the connectivity of the grid, and then the parameters of the transmission lines and equipment. So it's basically a reverse problem. So the reason that other groups, research groups in other universities, could not solve this problem was that there was basically a missing recipe that we found, and that is when you solve the equations are degenerate, which means that you have more unknowns than equations. So basically, you have infinite number of solutions, right? But one of the solutions is correct. So to find that solution, that unique solution which is correct, there was an equation missing, and we found that equation. And that equation is based on the second law of thermodynamics. It's called the principle of maximum entropy. So basically, it tells you that in a system, when you are generating and consuming power, the entropy of the system must be maximum at all time. And in a power grid, or in general in an electric circuit, the entropy is maximized when the sum of the admittances are maximized. And so this is what we found.
What is the reason we want maximum entropy?
It's a law of physics. It's
Okay.
it's the second law of thermodynamics.
So it's just a law.
Yeah, it's a law of physics, like the law of motion, or the other law of physics that we have.
It's what we have to work with.
Exactly. And it's a fact. And the reason that other people miss that is that it's kind of an interesting concept, because electrical engineers do not study thermodynamics in colleges. So, and we study a lot of things, but not thermodynamics. And because I love physics, I studied thermodynamics and the other things myself a long time ago. And that came to my rescue, basically, figuring out this key to solving this problem. But in any case, we solved this problem and we filed for a patent. And it was really interesting because there was no prior art. So the patent office didn't have any problem issuing the patent for us. And it took less than a year, which was very unique, because usually patents take years to be published.
What's an art?
Prior art. So so prior art means that nobody else has done it, or there was no even closely or remotely related issue or related topic to this problem. So usually, let me explain it this way. Usually patents are like this. You have a patent, and then you discover something, you patent it. And then you have an incremental improvement, you patent it, another incremental improvement, and you patent it, and so on and so forth. And then after, let's say, 10, 20 incremental improvements, you want to have another improvement. You have another improvement, you want to have a patent. Then the previous 20 times is called the prior art. It's a legal term in the patent office. And usually the examiner in the patent office, they have to go through all these prior art to make sure that what you are offering right now is unique and novel, right? Which takes a long time, because they're going to get back to you, ask question, okay, what would be the difference between this new approach and these issued patents? Then you have to explain in writing. So it takes a lot of time, back and forth, back and forth. So in our case, there was no prior art. So the examiner didn't have a difficulty to issue the patent in less than a year. So we got the patent in, I think, 10 months. So and now that was the easy part. Now the hard part is marketing and trying to basically show the application of this, because this is an academic problem, right? And nobody cares about the pure academic problem unless you have applications. And the applications are actually fantastic. And it was difficult for us because we are academics. Even my colleagues are academics, and we had difficulty to find the applications for this. So, but there are fantastic applications. Let me explain a few of them. So, for example, you have a transmission line, and this is close to home. It has a lot of applications in California. If you remember, in 2018, we had probably the biggest wildfire in history of California in Bay Area. It was called Campfire, and it caused $30 billion in damages. and 82 or 83 people died because of that wildfire. And it was caused by a transmission line, 125 kilowatt transmission line. That was so the transmission lines, particularly the high voltage transmission lines, are hooked to towers, right? And there are steel hooks that they hold the cables. And one of the hooks was 99 years old, and it was rusty, and it broke. It broke, and the transmission line was dangling for some time, okay, before the wind blew and disconnected the cable, and it created an arc and then wildfire. So if we had installed our technology, then before the cable was disconnected, we were able to find out that the impedance of the line or the admittance of the line has changed because of dangling. And then we could have prevented this disaster. So by just changing the configuration of the cables, you can detect that the change in the admittance, and then you don't know the reason of the change, but when there is a change, you can deploy a maintenance crew to figure out what's going on and fix the problem. So that's one of the applications. And because of that, we won California Energy Commission Concept Award last year.
Wow.
Yeah, which is a very competitive award. 200 plus startup companies participated in that. They have it every year. And out of 200 plus, I think it was 220 companies, only 28 were awarded. So, because of the fact that with this technology, we cannot prevent wildfires, but we can prevent wildfires caused by the power grid. Because wildfires, are caused by different things like lightning or even people. They can set fire, and so we can't do anything about them. But power grid related malfunctions that can be prevented with this technology. I'm gonna explain two more applications. There are probably 5-6 more applications, but I don't want to bother the listeners.
So before
ahead.
You continue,
Sure.
just how I understand it, the current standard of power grids is to use a software that takes different, maybe the type of material in the wiring and the distance and how it's coded and different parameters of the transmission line. And then it estimates what the resistance would be across that transmission line.
Correct.
But this Topolnet's patent would, instead of estimating just based off of parameters that the engineer or the user inputs into the software, would be reading the resistance and then determining what the resistance is, instead of assuming the resistance based off of parameters. And because it will know the resistance, it will know when a wire is dangling, which is infinite resistance, and then it will be able to cut off all power to that wire.
Yes, that's correct.
Okay.
Actually, when the cable is dangling, it's not infinite resistance, because infinite resistance means that the cable has been cut off completely. But we already have protective measures when a cable is cut off. We have relays, we have reclosers. They trip immediately when something happens. For example, a cable is cut off. But we have a situation kind of in between the normal operation and complete cutoff, where the cable is connected, but it's not connected properly. It's not secured properly. For example, it's dangling. So the hook is broken and the cable is dangling, which is very dangerous. Think about it. We are talking about 120 kilovolts, 300 kilovolt, 400 kilovolt of voltage. And so these situations, our software can actually detect that, okay, it's not completely cut off, but there's something wrong going on there. But your analysis was completely correct. And we can find the resistance, the impedance, by the measurements of the voltages and the powers. Okay, so we have the voltages, we have the powers, and we can find the resistance. Now, the key is that if you have the measurements of all lines, the current of the line, the voltage, everything, so that problem would be actually very easy to solve. But logistically, it's almost impossible to put a sensor on every line everywhere to detect the or to measure the parameters of the grid. So what we do is that we just need 4 different measurements from each bus: voltage, phase of the voltage, and active and reactive power injected to the bus. And that's basically the key of this software, because it requires minimum measurements. Now let me tell you another application of this, which is really exciting, and it's kind of related to what you analyzed. Typically, when you find the resistance or the impedance of the line, you take parameters like the diameter of the cable, the length of the cable, and so on and so forth, and you calculate basically the impedance. But the impedance is not a fixed number. It changes with particularly temperature. Okay, so when the temperature goes up, we have a phenomenon called sagging. So basically, the length increases, right? And then the conductance changes. Okay, so basically, when the temperature rises, the resistance of the cable increases. Okay, which means you cannot inject more power into the cable, right? Because you have more resistance. On the other hand, when the temperature drops, we have less sagging, the length is decreased, and the resistance goes down, which means you can actually inject more power and get a better efficiency from your grid. And the difference between the two is not small. You're talking about 20-30% change between them. Now, if you think about it, particularly in the North America, Canada, or Northeast, during winter, we have much lower resistance in the cables, which means we can increase the efficiency of the power delivery. So this is called dynamic power flow. So basically, you can change your power flow based on the impedances of the line. And our technology, because it finds the resistance of the cables in real time, in less than a second, we can update the operators. Okay, so the resistance has changed. They can actually use another software to adjust the power flow. For example, they say that, oh, okay, the resistance of this line has dropped by 20%, so we can inject 20% more power into that. And this is very crucial because the consumption of electricity is going up, EVs, the other electric equipment, and laying down transmission lines is very expensive. And utility companies don't want to do that. So we are offering a solution to the utility companies that they can use and increase the efficiency of the current equipment. So this is another application of this technology. And the last application that I want to mention is cybersecurity. So, which is very, very important in the current situation. So currently, the information of the topology of the grid is stored in the computers, and they are updated, not in a matter of seconds, but in a matter of days or even weeks. So, for example, if there is a change in the topology somewhere, then they have to manually go there and update the topology, the information in the computer system. Now that is very dangerous because hackers can get into the computers and change the topology information stored in a computer. And because the state estimators rely on that topology, and they see that the topology has changed, but it hasn't changed actually in the field, right? So they adjust the power delivery or power flow to compensate for that, right? Now, if the hackers are smart, they can change the topology in such a way that the software would react, change the power flow, and overflow one part of the grid. Okay, and that would create a cascade of blackouts. So, but by knowing the actual topology of the grid in real time, you can update it and then thwart the hackers' attack easily. So that's another exciting application of this technology that can be used for cybersecurity matters.
Yes, and that. So, what are the 4 inputs?
We need the voltage, the phase of the voltage, active and reactive power at each bus in the power grid.
So, voltage, phase voltage,
active and reactive power.
active and reactive power at each bus.
Yes.
What is the frequency of buses compared to the frequency of transmission lines?
They are the same. We have a sinusoid, and the frequency of the sinusoid is the same everywhere. It's 50 hertz.
Oh, when I say frequency, I don't mean electrical frequency.
Oh.
I mean how, for every one bus, how many electrical towers would you say there are?
Okay, towers are between the buses, right? So a bus or a bus bar is actually a piece of metal, and the connections are all connected to that. So that's why we call it bus. It's a bus bar actually, and so for example, we have a generator, and the generator, the cables come out of the generator connected to a bus, and from that bus, the electricity is distributed to different locations. And when the electricity gets into the location, for example, we have we used to have a power plant in San Onofre. It's turned off right now, but suppose that it's on. Then we have miles and miles of transmission lines to other cities, for example, to San Diego, to Los Angeles, and the other cities. And between these buses, when they are transmitting electricity, we have towers, and the towers hold the cables, right, until they reach to the destination. And at the destination, we have another bus. Okay, they're connected to that bus, and then from that bus, we have transformers that would lower the voltage and then distribute it in the city. Several levels of reduction of the voltage. So basically, this is the structure of the transmission system. So we have another system which is called distribution system, low voltage distribution among the houses and commercial places and stuff like that. So as far as I understood about your question, the frequency, you meant how many of these we have
buses are there, and how many towers are there?
Oh, there are many towers because they are basically holding the cables. But buses, well, it depends on. I think I don't have an accurate number, but for example, in California, I think we have thousands and thousands of buses. I don't know the exact number, but there are a lot of them. But in terms of towers, I would say you have seen the towers when you're driving, and the distance between two adjacent towers is like, I don't know, 100 yards or 200 yards. Now, if you have like a 100-mile stretch of the transmission line, you do the math and how many towers you need. So towers, there are many towers, maybe millions of them.
So inserting, these devices that would be able to read voltage, phase voltage, reactive power, real power, placing them on the buses would be much less expensive than any sort of device that reads input at towers.
Yes, correct. And those devices, which are, by the way, they're called Phasor Measurement Units, or PMUs. They have been installed in, I wouldn't say all utility companies in the US, but the major ones. For example, SDG&E, I think they have installed PMUs all over their grid. Southern California Edison, the same. PG&E, they are way behind.
Where's PG&E located?
Pacific Gas and Electric is they cover Bay Area and North California.
Okay.
So they are behind, and we saw the result in 2018. So right now, even for example in SDG&E or Southern California Edison, we see that the PMUs are installed everywhere, but still they are shutting down the power when there is Santa Ana wind, which is not the best way to handle this situation. To avoid wildfires, shutting off completely part of the grid. And so basically we have the solution. If this software is installed, they can actually monitor the health of the grid, and they don't have to shut down or shut off the electricity over a wide area, just to be on the safe side.
Would they? So my first question is, would PMUs, if there were PMUs installed on that 99-year-old transmission line that began dangling and eventually started campfire in 2018, if there were PMUs on that, would there have been any relay to the operators that this is a hazard?
Well, that depends on how the utility company operates. If they could actually detect that abnormality in the value of the impedance of that line, it depends on them. They can make a software or something like that to shut off that particular transmission line, take it off the grid. Or if the abnormal behavior is not very critical, they can just deploy maintenance crew to look at the tower and see what's going on, and take some steps to remedy that situation. So it depends. Afterwards, it depends on the utility and how they operate. But I think the best way is just to shut off the electricity before something happens, and then take a look at it and fix the problem.
Okay. But still, even with the PMUs, we do have an issue of not being able to maintain efficiency in high entropy states, such as high winds or possibly a cybersecurity attack. And with the device, what are these? What do you call these? Do you have a name for the product or your software or the idea? Is it TopNet?
Yeah, no. We call it BusID. So basically, the identification of the structure or the buses. With BusID, you can monitor the impedances and with the changes and everything, and then after that, you can use another algorithm to determine why you're observing changes. So the changes can be totally harmless. For example, as I mentioned, during day and night, the temperature changes, and you see changes in the impedances. So that's totally normal, right? But if you see a sudden change, which is beyond the acceptable boundaries, then there is something wrong. Okay, if the cable is cut off, that's a different story. So our software can detect that, but there are other protective measures already installed to deal with that situation. But our software comes in when the change is significant, but the cable is still there. It's not disconnected. Okay. So, which is very important in those situations that I explained, like if there is a dangling cable, or there's a cyber attack, for example, they change the information in the computer, but the topology is intact. Or in dynamic power analysis and dynamic power flow, where you want to use these changes for your benefit.
Okay. So when the wire is still connected, but there has been some sort of disruption in the infrastructure, the security of that wire, the PMUs can't detect that.
No, the PMUs just measure the voltages and powers. That's it. They are not smart devices. They're just, you can call them sensors. They're just sensing the change of the voltage, the phase, and the power. And you need to use that information, process it, and extract
useful data.
Useful information from it. And this is what BusID, our product, is doing. And one of the most important features of our product is that it's based on concrete and accurate mathematics. It's not now. It's a kind of a trend these days. We're using machine learning or artificial intelligence to detect this, to detect that. So our software does not work based off artificial intelligence or machine learning. It's based on concrete mathematical equations, and it's completely deterministic. It's not stochastic.
Okay, and that's in regard to how it's reading the power and reading the voltage.
Not reading the voltage, using the readouts to find the impedance or the resistance of the cable.
Okay. What do you mean, the readouts?
So these PMUs, they are sensors, right? Basically, and they measure. For example, we have a voltage, right? It's a sinusoid, and they take samples of this sinusoid with a very high frequency, and then they measure the amplitude of the sinusoid and the phase of the sinusoid compared to a reference. Okay, and they do it really, really fast. They parse like 60 measurements, 60 samples at each second. So And also they measure power, active and reactive power. So you have very fast measurements, and you have they also measure the frequency and a bunch of other things that we don't use in our software. And there are data streams from these PMUs. And by the way, one of the most important aspects of PMUs is that they are synchronized using GPS, because it's very important that when you receive the data in your mission center, the data, each sample has the correct timestamp. So if you use a traditional communication systems, for example, you have a sensor at 200 miles away or even 500 miles away, and another sensor 2 miles away. And because there is a delay in communications, in any communications, we have delay. We receive the data at different times. So you can't use the data that is received from 200 miles away with, let's say, 20 millisecond delay, and data that's received with a delay of, let's say, 100 microseconds at the same time, because they are actually showing events at different times. Okay, so you have to have synchronized data. And this happens in the PMUs because they are all synced using the GPS. So when they send the data, you have timestamp for each sample. And then you can compare it with the timestamps of the data you're receiving from other PMUs. And then you can sync the data and solve the equations, do the analysis. And that's why PMUs are very important. They're not simple measuring devices. They are synced through the GPS.
Okay. So does each data sample have a timestamp and a GPS location?
Correct.
Okay. And does BusID take in the PMU information?
Yes. So the most important part is the time synchronization. The location is important, to at the end to draw the map. But in terms of the analysis, timestamps are very important. We have to make sure that, for example, the voltage measurement that is coming from 500 miles away and a voltage measurement that is coming from 2 miles away, we have to make sure that these two were measured exactly at the same time.
Okay, that makes sense. And you do that, as you said, by verifying the timestamps are the same and the GPS. I mean, you're not worried about the GPS location necessarily, but the timestamps align and you got them at different times, so you know the distance.
No, we have to actually use the data that were sampled exactly at the same time. Now, we have a delay in communication. So, for example, you sample the data, let's say at exactly 12 o'clock, right? One sample, and one sample exactly at 12 o'clock at another bus, right? But they have to be transmitted through the communication system. So when you receive the data from 500 miles away, basically you receive that data after you receive the data from 2 miles away, right? But it doesn't matter because you have the timestamp. So you in the computer, you sync them up. You know that, oh, okay, so I received this sample a minute ago, but I received this sample 2 minutes ago because of the distance. But I sync them up in the computer. So I don't use them when exactly they receive. They have to be adjusted. And because we have the timestamps, we can sync them up. And that's why the algorithm works. Otherwise, if you don't know the delay or the delay is changing because of the communication systems, you will not be able to use this software. And this is old technology where there was no timestamp or there was no GPS information, which is called SCADA, which is an old-fashioned system that has been used widely in utility companies. but they don't have these timestamps accurately because they're not synced. Now with PMUs, we have this information, and a lot of people actually are trying to use the PMU data to extract useful information from the grid. And they're actually doing a great job in different aspects, finding this different aspects of the grid. For example, one very important piece of information that the PMUs provide is the frequency of the sinusoids, which is we always think that, okay, it's 50 hertz or 60 hertz in Europe, but the frequency changes. The change is not significant. So for example, it changes between 49.8 to 50.1, something like that. But if the frequency deviation is more than that, then there is a problem with the power grid. It's a synchronization of the generator or stuff like that. So PMUs generate a lot of data useful for different applications.
So BusID works in collaboration with PMUs to, that data all exists, the PMU data with the timestamp and the GPS location and the electrical specifications. And BusID works in collaboration with all the PMUs within the grid it's installed in to synchronize their data to be able to get a fully comprehensive picture.
Correct.
Of the grid. And then using that picture, another tool can be used to make adjustments based off of very sharp changes in frequency or some sort of specification that seems malicious, or maybe not malicious, but dangerous.
That's correct. So that would be actually the next step in our development, because when you see the changes in the resistance and impedances, you don't know the cause of those changes. Some of them are obvious. For example, between day and night, the temperature changes, and you have some kind of the oscillation that is synced with day and night. So you know that, okay, so this is because of the change of the temperature. But there are other things. There might be things that we don't know. Well, we have to deploy this, and that's why we are actually working with some utility companies to do pilot projects to see what we can extract from this information. Okay, and we have a lot of work ahead of us, but that would be the exciting part of this, because when you get the information, when you see the changes, finding out the root cause of these changes is a big challenge that we need to attack. And we need to use other algorithms or other methods to distinguish between the root causes.
What do you mean by different algorithms?
So, for example, suppose that you have a transmission line, and you're monitoring the resistance or the impedance of the line, right? And throughout, let's say, a few days, you see changes, right? Some of the changes are obvious, as I said, between temperature, day and night. So you see some kind of oscillations. But you also see some other changes that you don't know the cause of these changes, right? It might be, and they differ in different locations of the grid. So maybe there is a loose connection that causes these changes. Maybe there is wind blowing at some, just think about the big picture. We have, let's say, the state of California. We have, for the sake of the argument, let's say that we have 5,000 buses and, I don't know, 1 million miles of cables, which is not, I'm not actually trying to exaggerate the situation. It's something like that. And at each location, you have different phenomena going on: wind, temperature, and sabotage. You never know. So you are detecting the data. You are actually seeing the changes, but you don't know why you see the changes, right? So this is a big challenge, actually. And this is where I think machine learning would be really helpful to teach the machine learning for different scenarios and stuff like that. It's kind of a pattern recognition, analysis, and those sort of things. I don't know exactly because we haven't done it. We have to actually go to the field, gather the data, and then try to analyze the data and find the root causes. So that's why I said that this is just a beginning, basically.
Okay, that makes sense. And earlier, when you said that your technology isn't based on machine learning, you meant the reading of the specifications and determining the actual outputs. That is all based on physics, electrical physics. But as you know, and that's what BusID is currently. And moving forward, as this, as that tool is deployed in the field, as TopolNet gains more data, then that is when artificial intelligence, machine learning can be a tool that TopolNet uses to work with that data and provide users even more useful information.
That's correct.
Okay, that's very exciting. Good luck.
Yeah, thank you. Yeah, it's a beginning of the journey, and I'm really excited about it because this is very important. The health of the grid is very important, and it's a national security. And unfortunately, right now, the electric grid in the United States overall, it's not in a good shape in terms of monitoring and maintenance and stuff like that, and even cybersecurity, even sabotage. It's very prone to sabotage, and we need to do something about it. And this is very important.
Yes, and in case people, I'm not sure if you know, Professor, but have you heard of the 2015 Ukrainian Christmas blackout?
No.
Russia executed a cyber attack on Christmas Day in 2015 and blacked out a section of Ukraine, and it devastated the area for a short time, and it was pretty serious. People couldn't get cash out of their banks. People couldn't make transactions. Credit cards were useless. It's very possible, and it's very serious.
Yes. Well, I didn't hear about that, but that proves my point that it's very important to avert that kind of attack. And I know that I think it was last year or a year before, there was a cyber attack in one of the power plants somewhere in the Northeast in the United States. They infiltrated into the computer system, but they didn't do anything. Maybe they were just showing that they could do that. But we were lucky that they didn't do anything. But it shows that the system is vulnerable, and we need to do. There was a 60-minute program some time ago. They showed that you can completely shut down the entire U.S. grid by taking out like 9 transformers only, which was really scary.
What is the reason only 9 transformers can be attacked and shut off the entire grid?
Because you can, by actually removing one transformer. And why transformers? Because transformers are very critical, particularly high voltage transformers. They are big, and they basically connect different buses to each other. lowering the voltage or even increasing the voltage from the power generator to the transmission line. So if you take out one of them, the software, I'm not an expert in that area, so I'm just kind of explaining what I know. The system, the software, has to reroute power, because when you cut off one transmission line or a transformer, they have to reroute the power from other power plants or other sections of the grid. And then if another transformer is removed from the grid, then this rerouting becomes really erratic, and it could create a cascade of blackouts. And they did the analysis at the Department of Energy, and they found out that, in order to create a massive blackout, you need to just remove 9 transformers from the grid. And there was actually an attack in the Bay Area. Somebody went into the substation and started shooting at the transformer. But we were with the machine gun, and we were lucky that somebody was there for some reason, because it's in the remote area, nobody lives close by, and they called the police, and the police came, and the attacker couldn't finish his job, fortunately. But that's a problem, because most of these places are remote. There is no security. There is just a fence, and they can easily get into the substation by cutting the fence. And and if they want to, put police or guards, it requires a huge budget, because we have many of these substations in the United States. So being able to monitor everything from a remote area would be really helpful. See, okay, if somebody starts shooting at the transformer, then you immediately see if the utility company uses our software, the BusID, they can immediately see the changes in the impedance of the transformer. Oh, okay, something is going on. So they can call the police, or they can put camera and then see what's going on. There are different ways they can prevent that.
Yes, and then BusID could be, in addition to cameras, another layer of security. We want layers of security to technology, not just one solution.
Exactly. Yeah, especially we are talking about this is something really interesting for the public, that electric power grid is the largest system that mankind has ever built.
Wow.
If you think about it, we have millions of miles of cables. We have huge transformers, and these are all connected to each other. And even before we had internet, and that kind of connectivity that we have right now through computers, we had the power grid, which was the biggest network ever built.
Okay. Did the power grid also work in conjunction with the landline grid, or
you're talking about the telephone landline?
Yes.
No, they're separate.
Okay.
The power grid basically provides electricity. The landline is a separate grid. But the telephone landline, which is nowadays is kind of useless.
Yes.
It's not that critical, because what if, thinking about 20 years ago, what if your landline is cut off? I mean, you can't call anyone, which is not a big deal. But if you don't have electricity, even 20 years ago, think about it, hospitals, police stations, if they don't have power, then could be a lot of disruptions, or or you remember it in 1970s, there was a huge blackout in Northeast, and the next day when there was light, they saw a lot of looting and damages that people did to the businesses. So that's a consequence of not having, and we are so dependent to electricity these days. I mean, you can't even imagine living without electricity for a day.
How most people would have a tough time cooking, or even finding food. Restaurants would have a tough time cooking too.
Yeah, exactly. And then there are many people who have medical devices attached to them, like the oxygen masks or stuff like that. They are at home. I'm not talking about people hospitalized, and they depend on electricity. And actually, if last year, I think it was the Santa Ana winds in Southern California, the SDG&E or Southern California Edison, they cut off electricity to avoid wildfires. And one person died because she was using oxygen masks. She had some kind of respiratory problem, and because of lack of electricity, the device didn't work, and she died. So these things, are very important. Electricity, the security of the electric grid is very important.
Yes, it is very important. And just as a review, the original, so I think a lot of people are familiar with SCADA and
Yes.
how it's an industrial system. SCADA didn't implement GPS or timestamps within its data.
They have kind of timestamp, but the timestamps are not synchronized.
Okay, so then PMU was able to create a technology of synchronized timestamps, electrical specifications, and GPS location.
Yes, because of the GPS. Because the SCADA was developed way before the GPS era, and they didn't have that luxury.
Okay.
But now PMUs, we have the GPS, and it's fairly relatively cheap, so that's why they are able to synchronize data, and that's very important in our technology.
Yes, and so PMUs right now are probably the most advanced the standard of sensor technology for reading grid data available today.
I wouldn't say a standard because there are many smaller utility companies. They still don't have a lot of PMUs installed in their grids because, 10 years ago, PMUs were really expensive. Now the price has gone down dramatically, but still installation of PMUs is not easy, especially in the high voltage grids, because you have to get there and install the device at the 400 kilovolt transmission line. So they need to do a lot of preparations for that. But utility companies that are laying down new transmission lines, they can easily install PMUs without any difficulty because the cables are not, they don't have electricity yet, so they can just integrate it into their installations. Now we're going to do a pilot project with a utility company and they are actually laying down a lot of transmission lines, and that's why they are interested in our technology. So hopefully we're going to start the project hopefully next week, actually. And that's why they are very interested in this technology, because they can, while they are laying down the transmission lines, can easily install PMUs with no difficulty and then use them. And they have another problem, actually. And that's why they are interested in this technology. They have overgrowth of trees. It's a tropical country, and they told us that they cut the trees, after 6 months they grow back. So that's why they need to have kind of monitoring system to detect this overgrowth. Well, when the tree touches a transmission line, it's basically there are protections. It's like a short circuit, right? So they have protections. But when they are getting close to transmission lines, the resistance or the impedance of the line changes, right? Because we're talking about like 400 kilovolt, and then the tree is like 2 yards away from there is a leakage current between the line and the tree, and that will affect the resistance of the line. So that's why they are interested in this. I don't think they have a wildfire problem. Maybe they do, I don't know, but they told us that the tree overgrowth, the vegetation management basically is the reason.
But they probably also don't have as even close to as big of a grid as, say, California.
Yeah, absolutely. But they are actually growing. They told me that by 2023, they're gonna have like another 2,000 kilometers of transmission lines.
Okay.
And transmission lines, high voltage transmission lines. So 2,000 kilometers is a lot, actually, when you think about it. It's not just low voltage cables that you connect from the transformer at a substation to your house. That's easy. But laying down 400 kilovolt transmission line, it's a huge task. So laying down 2,000 kilometers is even a gigantic task.
What's the biggest difference in laying down a high voltage line compared to a low voltage line?
So in a high voltage line, first of all, they're called overhead lines. So they have to be at elevation to avoid arcs and sparks, because 400 kilovolt is a huge voltage. And they have to, if I'm sure you have seen the towers when you're driving between cities, and those towers are very secure structures. So they have to lay foundation for them. If you get close to one of them, you see a big concrete at the base of each leg. So they have to lay foundation and the structure of the tower. And even when they put the cables should be separated from each other. Otherwise, they can create sparks and arc between themselves. So it's every tower is a structure, and it's not easy to develop, to build. If I'm not mistaken, they say that it costs $2 million for each mile of transmission line when you want to lay down transmission. $2 million per mile.
High voltage or low? Okay.
High voltage. So now think about it. You want to connect two cities that are 200 miles away from each other. You do the math. So it's
$400 million.
Yes.
Okay.
So it's expensive. So when you're laying down 2,000 kilometers, so
wow, yes, very expensive.
Yeah, we're talking about billions of dollars of investment.
Wow, and that makes sense if they're investing that much into their power grid infrastructure, that they want their assets to be as secure as possible.
Exactly. So that's why our technology is probably more attractive to developing countries than the US, because in the US we have the transmission lines and they are installing PMUs, but because of the difficulty of the installation of PMUs on the grid that it's already working, many utility companies, they don't see the urgency of this. and they calculate the cost and say, oh, okay, you know what, maybe later. So
would you say PG&E, by not having PMUs in their system, made the wrong decision, and it cost
yes,
the whole Bay Area?
yes, and that was well, that wasn't because of not having PMUs. They knew the problem, and as I said, there was a steel hook, 99 years old.
Yes.
And they were supposed to replace them, but because of mismanagement and other issues, I mean budgets, they ignored it, and the disaster happened. And you can read a lot about the campfire, because the former CEO of PG&E was prosecuted, and he was actually found guilty a few months ago. I think it was March, if I'm not mistaken.
Wow.
And he was personally, he was lucky that he didn't go to jail, but he was fined like a few $1 million for personal damage. Now, I'm not talking about $30 billion damages that the PG&E had to compensate. That was kind of a personal criminal prosecution of the CEO. And as I said, he was lucky that he didn't go to jail. But that's the result of negligence.
Yes, it's very serious, and a lot of people don't realize how serious it is until something terrible has happened.
Yeah, and well, that's human nature. You can't change that.
No.
But it's very important. Power grid is very important, and securing power grid is very important. But unfortunately, utility companies are very slow in accepting, for right reason. I'm not blaming them, because power grid is a system that you can't just change. It's not like your operating system that you update it easily in 30 seconds. It's very difficult to allocate budget and do the maintenance. It's extremely difficult, and for an understandable reason, they don't want to change it, actually apply dramatic change. They want to make sure that, okay, this change is reasonable, because think about it, they are providing electricity to the public, and this is not an easy task. So their reluctance to accept new technologies is totally understandable.
What's the reason it's understandable?
As I said, because they're providing electricity to public, and when somebody comes in and says, like us, okay, we have a new technology which makes your life much easier, they would take it with a grain of salt. Say, okay, so you need to really prove it before we spend money and resources and start changing the grid. Because if we change the grid right now to the specifications that you like, what if your system doesn't work, and then we're gonna have blackouts and stuff like that? So for a right reason, they are very conservative.
Okay, that makes sense.
So basically, new technology has to prove itself that it is really important, and it is necessary, and it will not cause disruptions to the flow of electricity.
Hopefully, BusID can do that with the project.
Yes, that's our hope.
So one thing that you mentioned at the very beginning, and this, has to do with Topolonet, but more so, also related to your background as an educator. So traditionally, you have been an educator, and you mentioned you started Topolonet 5 years ago in 2017, and your partners at Topolonet are also educators. what have you learned in this experience after having the background as a professor in universities and then going into applying your knowledge along with bringing in, developing technologies which mostly revolve around software within, your education and then deploying that into some sort of profitable company?
Well, that's a very good question. Well, in academia, when you are doing research and you are attacking a problem, oftentimes you forget whether this problem, if you solve it, would be applicable to some real world systems, or if this technology can improve lives. Okay. So this is something that is, I think it's kind of lost in academia, particularly, I'm talking about engineering. Academia is very big. And we do a lot of research. We have graduate students, we have PhD students, we publish papers. But I have realized that many of these papers that we publish in prestigious journals, they're useless, basically. And I mean, in terms of their applications. And it's not like that, okay, so I have published a paper, I discovered something, and then this would be applicable in real life. No, most of the time it's not. And this is kind of unfortunate because I think that there should be a closer connection between academia in engineering and the real world applications, right? So we have different disciplines. They do theoretical work. For example, we have pure mathematics. They prove a theorem. It might not be useful, maybe useful in next 100 years. We don't know, but that's their job. I'm not criticizing them. That's very good, actually. But in engineering, my belief is that whatever you do should actually apply in real life and make lives better in the world. That's the purpose of an engineer, right? Not a pure mathematician or a physicist or a theoretical physicist. They want to decode the law of nature, which is very good. But engineers, our purpose is not to decode the law of nature. Our purpose is to use the information that we have, the mathematics, the physics that scientists have discovered.
The second law of thermodynamics.
Exactly, the second law of thermodynamics, and use them in an application. So we engineers, we build circuits, we build buildings, right? And that's the purpose of an engineer. And unfortunately, I see a huge disconnect between the way that academics in engineering departments think. And I'm not saying everyone is like that, but this is kind of a general trend. And the main focus in academia right now is okay, you need to get a grant and you need to publish. And it doesn't matter whether this publication is going to be useful someday or not, but at least it's useful for your promotion and tenure. And I think I don't know how, I have thought about it a lot, but I don't know how we can close this gap between academia and industry.
It's a huge problem. And I'm a UCSD graduate with a BS in electrical engineering. And when I went into industry, there's actually a kind of stigma in the San Diego area that engineers from SDSU are better right out of college than engineers out of UCSD because the work is so theoretical. They haven't had as much applicable experience. And it hurts, in the short term. Eventually, you gain that experience through, your profession and working. But in the short term, it does, I think, hurt the student.
Yeah, I'm aware of that stigma, and this is unfortunate. Well, at SDSU, we have a pretty good senior design, basically structured program. Well, it's not a program; it's a structured part of the. I don't know about UCSD. I'm sure that you also have some kind of senior design, but
Yes.
here at SDSU, we focus more on actually building something. So students build some. They don't do simulations or stuff like that. They build a circuit or something that is applicable to some real problem. And companies are actually donating money to different student groups. Not a lot of money, maybe $3,000, $4,000 for each project. And they also learn how to use that money wisely. So, which is very important.
In engineering, that matters a lot.
Yeah, and that's another thing that is missing in engineering programs. I don't know about UCSD, but we don't have it. Engineering economics, which is very important, because at the end of the day, if you build something which nobody would buy because it's expensive, it's useless, right? So it's very important for students to learn economics as well as the technical side. So, and this is a challenge because academia is geared more toward research and getting grants from the federal government, and they less and less focused on, the actual education of the future engineers. And as you said, you graduate, you go to work after 3-4 years, you gain experience and you will do fine. But we can save that 2-3 years in college, so that when you get out of the college, you don't have to wait another 2-3 years to gain the experience. So, but this is something that requires strategic thinking and concerted effort by everyone in academia and industry, which I don't see it's happening in near future.
No, what's the reason you say that?
Because as I said, in academia, the professors are under a lot of pressure, particularly probationary professors who are up for tenure and promotion. They're in a lot of pressure to get grants. And unfortunately, the metric to measure their performance is not based on the quality of the work. It's based on how much money you have gotten from the grants
Previously.
No. During for example,
okay.
They hire a professor, right? And the professor has 6 years to become tenure, right? If now that there are rules, okay, so you need to teach, you need to do research, you need to publish papers, and you need to get grants. It wasn't like that like 10-20 years ago. Now it's written, even officially written in the policies, that you need to have like an average of $100,000 in grants during the past 6 years. Otherwise, you're not going to get tenured. So, and so the professors are under a lot of pressure to generate money for universities. Okay. And to do so, they have to actually, and it happened a lot, you have to go outside your area, because your area is not attractive anymore. So there is not a lot of money in that. So you need to go outside your area because the money is there. So you have to write a lot of proposals to government agencies, NSF, DOD, to get some grants. And usually the success rate is like less than 5%. So you need to submit 20 proposals and if you are lucky, one of them would be funded. So that's why the focus of professors are not on educating students. They are on getting grants and doing research. And they have realized this, so they are actually changing the structure a little bit to hire professor of practices. They came up with this name, who are
at UCSD they called it a lecturer.
No, we have a lecturer, but professor of practice is a little bit higher than a lecturer, where there is a little bit more job security into that. The lecturer is like you teach a course in one semester, next semester there's no guarantee that you teach another course. But a professor of practice is kind of like a tenure or tenure track, but they're not going to focus on research. They're going to focus only on teaching and educating students. So they realized that there is a problem, and they are trying to solve that problem using this new model, which is good. I don't know how it'll work out, but at least it's a move towards a positive direction to close this gap. So they don't have to actually worry about, bringing money into the university, and they have to do research, they have to publish papers. They don't have to worry about those things. Their performance will be judged by their teaching record.
Okay, that sounds like a good new practice, new model. It's important, both of them, for institutions to be able to be well funded, to continue providing high quality education with high quality professors, but then also to actually educate students who are really there for less than maybe, say, a graduate student who doesn't, a graduate student to that researcher might be, there might be a good relationship, mutually beneficial, but for the undergraduate student who wants to be 4 years, get out, that sounds like a model that might help them.
Yes. One of the problems in research universities like UCSD, SDSU is also a research university, but UCSD is very extensive, is that because professors are so busy with writing proposals and doing research, advising PhD students, they don't have time to actually go to the classroom and teach. And I have heard that many times they send their TAs or PhD students to the classroom, to cover the lectures, and this is not good. And I don't blame them, because they're so busy with research, and sometimes they forget to even prepare for a classroom, or they don't even have time to prepare for the classroom. It's very difficult to teach 2 courses per semester at the same time, having 10 PhD students and 15 master's students, and writing 2 proposals per month. It's a daunting task. So that's why this model, I really hope that it'll work, so that we have professors who are 100% dedicated to teaching, and they don't have to worry about research. So that would be, as you said, that would be very helpful to undergrad students who don't want to go to grad school, and they want to go to the industry immediately after their graduation.
Yes. Well, Professor Ashrafi, are there any last words about what we've spoken about, be that Topolonet or applying engineering practices into useful context, that you'd like to leave our audience with?
No, I think we pretty much covered everything. Probably we didn't solve all problems in the world, but but that was a very nice chat, and I really appreciate inviting me into this podcast. And I don't have anything else to add.
Great. I appreciate you taking the time as well.
Thank you.
My guest today has been Professor Ashrafi. Thanks for coming on the podcast, Professor.
Thank you so much for having me.